So we were focusing on the development of grid operation for the real time, and we started this with by proposing what we call a power system traffic light. So we mapped the actual physical state of the grid on the phases of a traffic light, so green, amber, and red. And from this traffic light phases, we could derive operation modes that could choose more or less automatically the appropriate methods that were required to respond to the physical situation in the grid. Another advantage of this power system traffic light is that it clearly defines the interaction between the market and the grid, especially the DSO actions on the grid. And so we have proposed in the following, I would like to show you the results or the approaches we propose for the different phases of the traffic light. I just want to make a remark on the green phase, so what we call the normal phase. This is the very market-driven phase, and our focus lies really on tools for the DSO, so where the DSO is really interacting with the grid, and so we didn't look on this phase. But for the amber phase is what we call a critical phase. The grid is still working correctly, but there's places where the situation is deteriorating, where we have voltage limits that are violated. And with this optimization, we can bring back our grid into in a green state. And so we can optimize multiple criteria. So we can look on the voltage profile, we can look on the line loading, we can look also on power losses. And what we use for the optimization is then the flexibilities that are provided. So we change the set points of the prosumers to bring back our grid in a good situation. And this is we have done in this example here at a real grid here from Électricité de Strasbourg. It's the Breusdorf grid area, and you have the two feeders. And here on the plot below, you have the voltage of this grid. It's a 20 kV distribution grid, so it's plotted on per unit, so 1 means 20 kV. And here you also very clearly see the two feeders, and you see in blue that for the one feeder at a certain point, because the load is so high, the voltage limit is passed, so we have voltage that's too low. And then with the optimization, by using the prosumers that you see in yellow on the schema, you can bring back the voltage, especially by injecting reactive power, so that again the voltage limit is respected. This we tested in simulation, but we also tested it on the field. If you want more information, you can come to the Électricité de Strasbourg table in the exposition. There you see how we interacted with the real grid. Then we have the emergency situation, so the red phase. And the first question is, what are for us emergency situations? So it's very fast deteriorating grid states. So when we have, for example, very fast changes in frequency, or when we have outage of generators and or outages of parts of the grid, or if we have communication disruption, what is especially for our distributed system is quite a severe consequence. Or if we have inconsistent control signals, if, for example, the optimization is not working correctly and is sending set points that doesn't make any sense. These emergency situations, they might result from severe meteorological situations, from technical defects, or what is newly arriving from cyber attacks. What are now the fallback strategies we considered in the DREAM project? So to begin with, the decentral control structure itself, it helps us to cope with such situations. We also investigated local control of generators, so they not just can take the results of the optimization, but they themselves supervise the grid. And we also have, in some parts, implemented state estimation that to calculate the complete status of the grid that can handle false data to a certain extent. This actually we could not test, or we did not want to test in a real grid. So here we have a specialized test environment. And then we have another red phase, when there's already an outage occurred, so we call it the dark red phase. And here we propose some self-healing functionalities of the grid. So, for example, if there's an defect happening on the grid, then you see on the feeder here, for example, at Altenstadt 25, and then the circuit breaker at the feeder is opening, leaving the whole feeder unsupplied. And then our approach firstly starts to really find the affected areas, so by analyzing the fault passage indicators to isolate the affected area and then to resupply the rest. And this resupply is done by changing the grid configuration, by opening and closing switches. This actually we do not do in the project, so here these are the grid operators that will do it. So we propose in the form of a text a solution that then the grid operators can follow to establish the new configuration. And here in this case would firstly be to isolate the faulty cell, then to reclose the circuit breaker, and then to reestablish the supply for the rest of the feeder. And this function is running in parallel in the SCADA here in Strasbourg. So if there is a fault, the grid operators can look on our solution.